Hey everyone, my name is Alon and I'm the CTO at Aporia. And today we will talk about recommender systems in production. And more specifically, we will discuss how to utilize insights from production data, so recommender system actually running in production, in order to, one, improve their performance, two, actually increase the revenue that we see from these models, and then three, which is also important, and is how to reduce the inference costs from these production models. So we will use the production data, meaning the inputs and outputs from these models, in order to do all of these three things. So just to give a little bit of background about recommender systems. So recommender systems are everywhere. So let's assume that I'm looking on this product on Amazon. And if I just scroll a little bit down, then I can see, these two lists. One is smart home devices for you, and the other is, similar items that the other customers also bought. And these two lists are, with very high likelihood, these are actually recommender systems running in production. So each one of these lists. And just going back to the homepage of Amazon, we see things like personalize your device, deals on frequently repurchased item, recommended magazine subscription for you, and so on. So all of these are probably powered by personalization and recommendation models. So how do they actually work behind the scene? So let's assume that we have an e-commerce website, and we're looking on an item, and now we want to see, a list of what other items customers also purchased. So the website will actually send a request to the recommendation engine, and recommendation engines are very typically split into three different phases. So the first phase is called candidate generation. So, when I'm looking on videos on YouTube, there are billions of options of candidates for videos that could be in the sidebar, right? But the model cannot run on all of the different candidates. So the candidate generation kind of filters the data and basically provides us with some candidates that are likely to be relevant, even usually before the machine learning model actually runs. So this is the first step, usually within a recommendation engine. The second engine is actually, this is usually the main machine learning model. So for each candidate items, we want to predict what's the probability that the user will click this item or buy this item or listen to this song or watch this video, and so on. So this is usually a scoring model. And then the final part is usually called re-ranking, which is kind of deterministic logic to make sure that there is some diversity in the different recommended items. So this can be lots of different rules. But basically, we want to make sure, for example, that not all of our recommendations are shoes, right? Or things like that. So this very typically includes deterministic rules to actually control the predictions generated by the machine learning model. So this is very high level on how recommender system looks like. And some of the challenges with when you are actually deploying recommender system to production. So challenge number one is that the scale of data can be huge. So the scale of data can be very hard to analyze. So it can be very hard to actually, realize insights from the data. And not only that, but since the scale of data is so huge and there are many requests to the recommender system, one of the problems is that the cloud costs of the model inference can be super high. So while some predictions are extremely valuable, so some predictions of the recommendation engine actually lead to purchase, other predictions are completely not relevant. Someone just browses the website and they don't have any intent to purchase, for example. So these predictions are not relevant. And recommender systems usually are measured with special performance metrics. So with traditional ML models, we have metrics such as precision, recall, accuracy, which are relatively simpler to calculate. But then a recommender system, we want to take into context the search itself and the order of result within search or similar in other use cases. So there are special metrics for that, like NDCG, precision at K, which could be very difficult to implement at scale. So these are just some of the challenges of recommender system in productions. And again, if I go back to our goal, so our goal is to use insights from our production data, from the logs that the recommender system generates in order to improve the model performance, to increase the revenue from the model, and then also to reduce the inference cloud costs. So how are we going to do that? The first step would be, we need to analyze this data, right? We need to analyze the data generated by the recommender engine. So we need to make sure that it's stored somewhere. So let's say I have the e-commerce website and we are running recommendations from this website. So there is a request to the Rexis model. So some of the features could be price, browser, category, country, and so on. And the Rexis model sends back the items that should appear in the website as recommendations. So what we want to do as a first step is to store these inputs and outputs of the Rexis to a data lake or a data warehouse. So in this case, we've chosen BigQuery, but it could be Snowflake or Databricks or any your enterprise data lakehouse that you're using. So this is the first step. And usually you can also take additional information, such as when the user actually clicked an item, or maybe even added the item to cart, or maybe even purchased it. This is something called delayed feedback, or kind of ground truth, right? So if we recommended something that the user actually clicked on and purchased, this is a very good signal that the recommendation engine works as expected. So we want to store this data as well, right? So essentially we are storing the inputs and outputs of the models as well as the delayed feedback. And on top of your data lake or inference store, you can basically add a model monitoring system to start analyzing this data at scale. So how does connecting Aporia, which is a model monitoring system, to your inference store looks like? So the first step is really to choose the data source. Your data source could be Databricks or BigQuery or any other database. You can actually write a SQL query to fetch the information and then map the different columns. So maybe some of the columns are features, some of the columns are predictions, and some of the columns are delayed feedback, as we've discussed before. So after the model is actually integrated in Aporia, you can actually build a dashboard around it. So you can understand what's going on and see, maybe on a weekly cadence that the model is working as expected. So essentially, you can add your custom metrics. You can write Python code to add your custom metrics or business metrics. So for example, if this is a recommendation engine for items to be purchased, there is some ways to measure proxy of the revenue from the model, for example. So this is one example. Another example are data segments. So maybe we want to split the data from the model and understand them in different segments of the data. And this is how it could look like. So we see the NDCG in this case for clicks, add to carts, purchase, and also the top drifted features. And we can also see different insights from the model. And this is something that we will discuss in depth in a second. So even if you have dashboards, one more thing that you want to set up are alerts, right? So when you have data drift or prediction drift, or when the model starts drifting or its performance starts degrading, you want to know about it so you can actually improve the model in production. So Aporia lets you very easily set up these alerts and connect to systems like PagerDuty, Slack, and so on. And essentially, you can track from the activity of the model to missing values, value range, performance degradation, and so on. So let's actually see what are some insights that you can get for your recommender system from Aporia. So let's say that the user is currently looking at a shirt, at a t-shirt, okay? And this t-shirt is obviously complemented by shoes and hats and things like that. And it's similar to other kind of t-shirts, right? So the recommender engine might recommend complementary items and similar items. And in this graph on the right, we can actually measure the conversion rate for complementary items and similar items, right? So the blue graph represents the complementary conversion rate and the light blue graph represents the similar items conversion rate. And this is based on the data from the model, on the logs generated by the models, as well as the delayed feedback. And essentially what we can see here very clearly is that similar items convert way less than complementary items. So it's actually better to recommend complementary items rather than similar items. That's what we learned from this graph. So this is the insight. And then the action from this insight could be, let's start recommending more complementary items by filtering a percentage of the similar items. So this will actually lead to increasing the conversion rate and revenue from the model. In practice, this can be done as part of the re-ranking step. So let's say that we receive our recommendations from the model. So we can add a deterministic rule to actually filter some of the similar items to make sure that we always have a little bit more complementary items. And this, from our data, should actually increase the conversion rate from the rexes. So this is an example for an insight that you can get from Aporia. And let's talk about another interesting example. So in this case, we see the conversion rate as well split to different product categories, right? So the purple one represents coats, the yellow one represents ties, and each line represents a different product category, right? And what we can still very clearly see, while most of the conversion rate is more than 0.2, we can see that ties almost are not converting at all, right? So they are just not converting, and really the action plan here is simple. We want to generate less tie candidates for accommodation, and by doing so, we will increase the conversion rate and revenue from the model. So if we go back to our here, then in the candidate generation phase, we can actually just generate less ties as part of the candidate generation. So we've seen two a little bit similar insights that have action plans that are kind of in separate pipeline. But let's take a look on a more interesting example. So here we can see two graphs. The left graph actually represents the volume of the model by region, right? So we can see different countries from US, Estonia, Germany, United Kingdom, and so on. So this is the volume of the model, the amount of predictions. And then on the right graph, we can actually see the revenue by this region. Right, so we can see, for example, that the revenue from most of the countries is pretty high, but the revenue from the blue country specifically is very low. So we can see that the blue country has large volume of data, but it has low purchase rate, right? So it has relatively very low purchase rate. So what we can do essentially, and this might happen because maybe our target market of the e-commerce website is just the US or just US and Europe. So actually Estonia is not a relevant market for this website. And what we can do is, instead of running the full-blown machine learning recommendation system, we can actually use a maybe simpler algorithm or maybe even a random sample in markets that we are not really selling to, right? And by doing so, we can actually cut the cloud costs of the inference of the model. So as part of the scoring, we can actually make sure to simply cut the cloud cost by using a simpler algorithm for specific data segments that are less likely to actually generate recommendations. So this is another example. So I've seen a question from the chat. So let me read it. For ties, maybe we should also check if ties in general are being sold or not to see if there is some correlation with less conversion rate as part of the recommendation items. Yeah, absolutely. So you can add, so in this, we kind of demonstrate them simpler, I guess, examples. But there are lots of more kind of monitors and rules and insights that you can understand by diving deeper into the data. So definitely, hope I answered the question. And let's take a look at another insight. So here we can actually see a little bit of a different insight. And on this graph, this is actually from an alert. And what we can see is that we have a prediction drift, right? So the blue graph represents all the predictions, the histogram of the prediction in platform equals desktop. And the purple graph represents segment platform equals mobile, right? So here we are comparing the prediction for mobile versus desktop. And we definitely see that there is some kind of drift, which is interesting. So basically, from this alert, we can actually dive deeper, and we'll see in depth how that looks like. But we can dive deeper to actually see what are the top drifted features, right? So if something with the prediction has drifted, then it's very likely that the features themselves were also drifted. So what is the insight? So essentially, we can see that the previously interacted feature started receiving incorrect values on the desktop due to a bug, and this led to prediction drift. So maybe this needs a little bit of background story. So essentially, this is based on a real case, by the way, that we've seen. So essentially, what happened here is that the recommendation engine has a feature called previously interacted with. Okay, so if you think about it, it could be very relevant to add to the input data what items this user actually previously interacted with. And what happened here essentially is that engineering kind of introduced a new e-commerce version, a new version of the e-commerce website. And then suddenly it just restarted receiving incorrect value or missing values. And basically the model just says, okay, let me predict anyways, and then you have a prediction drift. So the action plan here is actually fairly simple. We need to fix that bug. But this is kind of an invisible bug that's very hard to catch from systems like Datadog or New Relic, just because the system worked. Like there were no exceptions, nothing like that. So this is a data bug, which is very hard to catch usually. So here our action plan is similar. We want to fix that bug on the website. But this is kind of a few examples for lots of insights that you can understand by analyzing your recommender system data. And from a system, and usually this is a large scale of data. So using a system such as Aporia will let you do it very easily. So let me actually show a little bit how it looks like in practice. Let me see how can I share my screen here. Okay. Okay, hopefully you can see my screen now. Should be okay. Yeah. So this is how Aporia looks like. And essentially what we can see is all of the different models that we are monitoring in production. So we can see different models like search ranking to production recommendation to product recommendation, as well as other kind of models like fraud detection and so on. And essentially, even though this the solution is hosted in the cloud, the data does not leave your cloud environment. Okay, so the data is actually not shared with the cloud software, which is very important because for some of these models like customer LTV and recommendations and fraud detection, the sensitivity of the data could be very, very high. So you don't actually want to share this data outside your data lake. So one of the cool things about Aporia is that it runs on the data lakes, on Snowflake, Databricks, BigQuery, and so on. So here we can see kind of a high-level overview for the models. And in general, we can see, for example, if we have an alert in some model. So let me actually dive deeper into this search ranking model. And essentially what we can see right here is essentially the homepage of that model in production, right? So the data scientists, the person who is responsible for the model and is actually most familiar with the model because they spent, months researching the data and so on. So they can build dashboards for the data that they care about, right? So they can actually really customize what they are seeing for each model. In this case, let's try to visualize MDCG, which is a very important metric for our ranking models. So they can very easily see that not only across all of the data, but also for specific platforms or different data segments. So here we can see the MDCG for web versus Android versus iOS. And actually we can see that Android performs a little less well than other platforms, the yellow one. So this is just an example, but each data scientist and also each stakeholder, so maybe the business persona wants to see something completely different than the data scientist, so they can actually add a dashboard, call it ML recommendation product, and they can build their own dashboards. So the dashboards sound nice, but one of the things that you want to do usually is to get these, to know about these issues or insights proactively, right? So you don't want to look on these dashboards all day. And when you have an issue in production, Aporia will provide you with as much context as possible. So it will tell you what model was problematic. Can actually zoom it in a little bit. So what model, what was the drift score in this case? This is the prediction drift. So when did it happen? And also on what segment specifically? So this prediction drift actually happened for platform equals well. So you'll get a lot of context about alert, but usually that's not enough. Like you want to dig even deeper, right? To dive even deeper. So what you can do is to click the investigate button, and this will get you to the investigation room, right? So the investigation room is kind of this collaborative place where different stakeholders, maybe the data scientist, the ML engineer, data engineer, and so on, they can collaboratively investigate the issue together and also have some kind of audit. So months later, when there is a similar issue, they can actually go back in history and see what happened. So in this case, we see when the drift started, right? So I can actually go over different points and see the drift in time. So in this case, we see that the drift was very high at April 26, and then it got lower. So usually the first question is when the drift started. Another important question is, okay, the prediction was drifted, but what were the top drifted features, right? And we can see very clearly that the platform feature, which could be desktop or mobile, for example, so this is a highly drifted feature, input feature. So we have asked ourselves from the alert. So we've received the prediction drift alert. So we've asked ourselves when the prediction started, and then what is the top drifted feature. So to really get to the root cause of the issue, now what we can do is actually to slice and dice the data to get to the real problem, right? So let's take an example of how that looks like. So here we can actually analyze different segments of the data. So right now we are looking on country, right? And each kind of box here, each rectangle is actually a different country. So this is Great Britain, this is United States, this is Israel, this is Germany, and so on. And the color represents the metric, right? So when the score is green, then it means that the performance is all good. But when you have a red or yellow rectangle, then it means that the performance is less good, right? It's closer to zero. And we see that most countries have, their performance is okay, right? Most of them are green. Some small countries have negative performance, but essentially, we can see that there is a very large segment of the data, Great Britain, that is actually with low performance. So this is a sign that something here might be problematic. So from here, we can actually dive deeper and understand what happened within Great Britain. So we can click on the supply filter. And now we can see that within this country, browser equals Firefox. Okay, so from the different browsers, then Firefox specifically had an issue, right? So most of them are green. So this is Chrome, this is Safari, this is other browsers, and this is Edge. But we can see Firefox specifically has really low performance. So this is interesting. So within Great Britain, there is an issue with Firefox. So let's even dive deeper. And one of the cool things about Investigation Room is that this is completely collaborative. So I can add here the insights that we understand. Seems like it's only within Great Britain. And this is important usually for auditability and so on. So now that we have understood that there is an issue in Great Britain and Firefox, now we can really get to the problem. So we can see that essentially in platform equal Android, the performance is just zero, right? So this usually means missing values or something completely wrong. And we've just kind of understood the issue. We realized together, when the drift started, what were the top drifted features, and what is the specific segment of the data that was problematic. So we've understood the issue, and now we can basically go and see what's going on with the software for this. For example, one of the common things is a release of a new version for maybe an A/B test that runs in the United Kingdom, and it had bug on Firefox and Android. So these things happen, and they are very, very, very hard to catch, especially within the realm of ML models. And now that something like that happened, I can configure another monitor. Hopefully this also answers another questions from the chat. But now you can go ahead and configure a monitor for this model for detecting data drift or performance degradation for this specific segment. Right, so each one of these things is highly customizable. You can even write your own Python code via the custom metric monitor. But essentially, you can define your own data ML monitors for the model. So hopefully this was kind of a brief on so let me actually share the summary slide here. Then we can go to questions. So the summary is that essentially Aporia allows you to centralize all your ML models under a single pane of glass. So integration is simply as writing SQL on your data lake. And then you can get the custom dashboards and metrics and monitors and so on. This is number one. Number two is to actually gain insights to maximize the business impact from your models. So by monitoring different segments of the data, you can actually increase revenues for specific highly valuable segments and cut cloud cost in underperforming segments. So this is, two sides way of how you can really improve the performance as well as cut costs. And then when you have an issue or when you have an underperforming segment, instead of going to your Jupyter notebook and start DF and kind of slicing the data in a very manual way, within a few clicks, you can really get to the root cause of the issue, usually very quickly. So yeah, thank you very much. I think we have some time for questions. So let me go over them in the chat. Let me read. I assume the rank suffers from statistical size of the sample and systematic choice of hyperparameter source of errors that are hard to the model. Do you have an experience reshuffling the rank by fudging the scores of multiple sample? Yeah. So essentially, these are kind of, I would say, small tactics that you can try and see for your data. This is highly dependent on each and every use case. Okay. So essentially, it might work in some cases, and then for other cases, it could be very random, I guess. So this is usually something that you would want to A/B test and see what works better. So I wouldn't say there is kind of a specific trick that always works. These things are always kind of, it really depends on the use case, on the on the specific recommendation engine, and so on. Does the platform also allow us to catch data bugs like drift in the features themselves? Yeah. So we've shown that that you can basically define data drift monitors and prediction drift monitors and so on. Yeah. So essentially, you can track all of these sorts of data issues on top of your models. So another question, is the size for each box green, yellow, red based on total recommendations? Yeah, exactly. So the sizes of the boxes is based on the volume of predictions. So for a recommender engine, that would be the amount of recommendations. And the color represents the performance in that specific segment. So essentially, when you have a large square, with a very red or yellow performance, then you want to kind of dive deeper into that segment. And maybe we can just kind of show that. Yeah, I think if you guys want to see that again, just let me know in the chat. So another question, what about using LLM to restrict recommendations to the customer request? For example, I need an outfit as best man for my buddy's wedding, suggest selection of tuxedo, but yeah. So using LLMs for recommendation is actually really smart. So usually the flow looks like this. You can take the search query or even the product description or even the reviews or anything like that and pass that to an LLM, but not to generate more text, but rather to generate embeddings, right? So you can take the user query, and from the user query, you can generate embeddings that you can later pass to your existing recommendation system. So the recommendation system will not only be based on tabular features like price and category and so on, but also from embeddings from the text data or maybe other unstructured data. Just to give you another example, you can build a really smart recommendation engine by combining embeddings from text, from images, and from the tabular data that you have for each item. So maybe the product image, search query, and so on. Yeah, so this is definitely something that we are going to see more and more people doing, definitely. Just to share it with you an example that is really fun for this example. So, in Amazon, you can write maybe something like, I'm going on a hike or something, and then it will actually recommend to you the items that you need for that specific hike in that specific season, right? So the recommendation engines are going to get really, really good, especially with LLMs. Another question was about does the visualization of feature drift vary between table of features, embedding features of images, and etc. Yeah. So essentially, for unstructured data like images, text, and so on, usually it is very common to essentially investigate different embeddings. And to do that, what you can do within Aporia is really to visualize the embeddings within kind of, you can reduce the dimensions. Usually embeddings could be 1,000 dimensions, right? So you can actually reduce their dimensionality to 3D. So you can actually visualize different embeddings and actually visually see drift in 3D. So this is definitely something that you can do within the platform. And this is very useful for unstructured data like images and text and things like that. Perfect. So thank you very much. If you guys have any question, I'm available on LinkedIn and Twitter. Feel free to reach out and chat. And thank you very much.
Thanks so much, Alon. Thank you everyone for joining.